rotational kinematics, and so the only thing left now is the kinetic equation for rotational motion. So that's what we'll consider in this lecture. So this goes under the title of Eulerian mechanics. And this is the counterpart to Newtonian mechanics, which is the kinetic, which develops the kinetic equations for translational motion. So this is kinetics for rotational motion. Okay. So the picture that we have is your inertial frame, the aircraft, and we have an elemental mass there. So the position vector, we have a reference point P. That's where we are going to measure the angular momentum from. So the location of the position of the point P is vector rho. That's the inertial location, or the position vector of P. Location of the elemental mass dm relative to P is sigma. And here we have the center of mass. So that's the location of the center of mass, r sub c, and the relative position of the elemental mass from the center of mass, which is c, is r. Okay. That's the geometry. And as you know from definition, the angular momentum of elemental mass with respect to point P is sigma cross dm, sigma naught. That's from definition. And so, of course, the total angular momentum of the entire object is the integral of this, the sum over the body of the aircraft, is that. Great, so on this equation 1. Now we have derived before that the rate of change of the angular momentum, the inertial rate of change, is the moment measured from point P plus a compensation term to account for the motion of point P itself. This equation was derived in the previous lecture, lecture 5. Okay, so where of course your location of the center of mass is nothing but the weighted location of the entire object. So this is 1 over m integral r dm over the body. And the total moment acting on the object is integral sigma cross dm. So this is the most general form of the kinetic equation. So this is the most general form. We are going to make this more palatable to computation and to implementation, because inertia is hiding somewhere here, right? All kinetic equations, we are doing kinetics here. So all kinetic equations require inertia. So we're going to have to extract the rotational inertia from here. So that's what we're going to work on today. So we're going to take this and we're going to start making some simplifications. So we know that you can extract Eulers equation, which is written casually as the inertial rate of change of angular momentum equal to torque or moment, only if, I think I missed something here, there's a cross product, of course. Only if this compensation term is 0, and that will happen. So the rate of change of angular momentum, inertial rate of change, is going to be equal to the moment only if rho dot is equal to rho double dot is equal to 0, which is the case when P is inertial. Or we see another special case emerge from here. If you decide to move the reference point P to the center of mass, then also you get that the rate of change of angular momentum equals to the moment. Right? This is the Eulers equation. The Eulers equation can be had if our point of reference P is nothing but the center of mass. And that's what you see in a lot of textbooks, that they just give this equation, but behind that equation there is something more going on, right? That equation holds in a couple of, or well, 3 different cases. Another case is when a weird case arises when the point may not be inertial, so this is non-zero, and neither is it the center of mass, so this term is not zero either, but somehow the way point P is moving relative to the center of mass, this cross product ends up being 0. So I'm just going to call it the weird case. This is most likely not going to happen, right? This is much more realizable, and that's much more realizable than the third case. So this equation is given in textbooks, but it sometimes they do not state that it holds only if the point of reference P is either inertial, or, which is more a more common case, the point of reference is taken to be the center of mass. So we're going to have these cases now. So we will consider choices for the reference point, right? P being the center of mass. This is the most common, like I said. Inertial point. For example, O. Right? Where's O? That's inertial point is the origin of the inertial reference frame. And this is the third case, most unusual. We'll look at these 2 cases. And further down in the course, in fact, after a few lectures, this one is the only one we'll focus on, because that's what is done in developing the equations of aircraft motion. Okay, so to begin, let's go back here. To begin, we are going to set, okay, and try and construct the angular momentum vector. So what happens when P is dragged down to the origin, we get that rho is 0 and sigma is equal to r, kappa, right? And therefore, the angular momentum of the object measured from O is r cross r dot d. Right? So now we expand r. Note that r is nothing but rc plus the relative vector little r. So the location of the center of mass plus the relative vector cross with right. So if you open this up and make simplifications, I'm going to come out here. So open this up and we get RC does not change as you integrate over B, right? We have discussed this before. So because RC is a point that is not going to change as you make this, as you span over all the elements of the mass. So you can just pull that out and all terms involving RC. So when you pull these two, when you consider these two, that product, that entire product comes out and you simply get integral over dm, and that's the total mass. Right, that's the first term. plus RC cross R dot dm plus R dm and the final term now. Of course, this you can't do much about because the vector R will change as you span over the entire body, right? It is the location of the elemental mass with respect to the center of mass. So it very much depends on where the elemental mass is located. So as you span over it, we can't pull that out. Now, we have seen before from the previous lecture that this term and that term are both 0. And so what we get is that the angular momentum of the object measured from the origin is equal to that plus so this equation is interesting, right? This is the total angular momentum of the aircraft, and we haven't made any assumption about it being rigid, at least so far, right? So this equation holds for non-rigid aircraft. So what we're saying is that the angular momentum of the entire aircraft measured from point O has two parts. This is the angular momentum of what? Of a particle of mass cap m, that's the entire mass of the aircraft, located at RC, which is the location of the center of mass. So essentially this is angular momentum of the center of mass with lumped mass m at that point. Right? So it's the angular momentum of that particle. And what about this term? If we go back to the definition, remember the definition was what? About some generic point P is sigma cross sigma dot dm. So if sigma is R, where is P? If sigma is R, then P must be C, right? So this is the angular momentum of the entire object as measured from some point P, but if that point P were the center of mass, then you would get that, right? So this is nothing but the angular momentum of the entire aircraft as measured from point C. Right? So we get a very interesting equation which says that the angular momentum of the aircraft measured from the origin, which is an inertial point, equals angular momentum of the particle located at the center of mass carrying the entire mass of the aircraft, right? It's that particle angular momentum plus the angular momentum of the aircraft as measured from that point. So this is a nice little expression. And like I said, this holds for all objects, including non-rigid aircraft. Okay. Now, if we want to go any further, so this is how far as we can get. This is an abstract equation, as you can see, has not been expressed anywhere, right? And so in order to go further, we must expand this term. By the way, all these derivatives, right, are inertial derivatives here. So I'm being a little sloppy, but by now you know what I mean here. In the definition, the derivatives are all inertial derivatives. So in order to go further, we must expand that term that's contained there. So we have contained here, angular momentum measured from C is r dot dm. We need to be able to expand this out. Great, so the way to do this is we know that the inertial derivative can be expressed in terms of the body derivative through the transport theorem. So the body derivative plus omega cross r, where, so here's the notation, is the angular rate of the body frame with respect to the inertial frame, right? And we've had this discussion before that if now we assume the object, the aircraft, to be rigid, right, then this term must go to 0. Why again? Because if what we are saying is that r is the relative position of the elemental mass relative to C, right? So if you were sitting at C, right, if you're located here, that's the position of the elemental mass you will see. Now while sitting there, right, if you have a sensor with you and you are sensing a velocity of this particle, of this elemental mass, it means that the elemental mass is moving with respect to the object, with respect to the center of mass, right? So it's not rigid, right? So if this were non-zero, meaning if you sense a velocity as while sitting at C, then you are sensing different parts of the object moving in different directions. So your object cannot possibly be rigid, right? It needs to move as a single structure. So if the aircraft is rigid, then while you are seated at C, right, at the center of mass in the body frame, you will not be able to measure any velocity of any elemental mass. So the inertial velocity of this relative vector is equal to omega cross r for rigid aircraft. So moving forward, we're going to plug that in over there, and we're going to, from this point on, make the assumption that the aircraft is rigid, and we're going to make that simplification, right? So for rigid aircraft, right, so I'm going to put this in there. The angular momentum of a rigid aircraft measured from its center of mass is r cross that inertial derivative, and for that we have omega cross r integrated over the body. A super useful expression. Okay. So we do some tricks here. I can actually, to make it more palatable to implementation, just flip this around so I can pull out omega, right? Omega is the rate of rotation of the body frame with respect to the inertial frame, so it won't change as you integrate over the body, right? So we want to be able to pull it out, so either move it to the right or to the left, right? So it's stuck in the middle right now. So we flip this cross product, and when you flip the order of the cross product, all you need to do is compensate for that by adding a negative sign. So this becomes equal to cross r cross omega dn. Right. Now this is still not okay because it's hard to pull this cross product out, right? So that's where we have talked about earlier, the way in which you express these relationships, it makes a difference. Right now it is in a vector form, right? It's a cross product. So if you are able to express this cross product as a matrix multiplication, then things will be much easier and you'll be able to slide that omega out. So let's do that next. So we remember the skew symmetric form of the cross product. So for that, of course, we need to express these vectors in a frame. So go back, plug that in over there to the top, and we get, for a rigid aircraft, the angular momentum measured from point O equals this particle momentum, angular momentum, minus great. Right? So like I said, we want to be able to do more with this, and we can't until we express these vectors in a certain frame. Right now this is abstract, right? Not expressed anywhere. So we're going to use the B frame to express or coordinatize all vectors. And so we say that let R, B have the following coordinates: X, Y, and Z. So that's the same as X B1 plus Y B2, Z B3. These are the amplitudes of the unit vectors of the B frame. And as before, the angular rate expressed in the B frame, we say is P, Q, R. Okay. Now recall that when you have this cross product, right, this is equivalent to the skew symmetric matrix associated with the A vector where the skew symmetric matrix is so we are going to use that trick here, right? Like I said, we must first express everything in some frame, so we have decided to use the B frame. So let's do that. So we get the term inside the bracket, RB, omega B. This becomes, following this approach, the skew symmetric matrix associated with RB, omega B. Right? And then there is another cross product, that with the whole thing here. So R cross is skew symmetric associated with that, and then this. Right. And so here's what we get. This becomes equal to, using the components that we have defined, 0 minus Z, Y, Z 0 minus X, minus Y, X 0. The same. And then omega B, which is PQR. Right. And so this term right here, remember this is nothing but HC, right? The angular momentum measured from C. Now we have expressed everything in the B frame, so this vector gets expressed in the B frame automatically, which is equal to minus R. Throw that in here. Oh, express everything in B. And we get integral of this whole thing, right? dm. And when you carry out that multiplication, so now you can pull out this vector omega here, right? Because these terms are the only things that are changing as you integrate over B. The omega term just pulls naturally out. It's the multiplication of these two matrices, right? And you get minus integral over B when you do the multiplication. And the whole thing multiplied by that, which is omega. Right? And we all know what this matrix is called, right? It's a matrix of integrals involving these terms. This is known as the moment of inertia, which is usually given to us. Now, this moment of inertia is measured with respect to where? With respect to C, measured by C, and expressed in B. That's the body frame, right? Because these coordinates, x, y, z, arise when this relative vector measured from C was expressed in B. So there are two things that are important when we are talking about angular momentum, right? Where it is measured from, so what's the reference point? That's C. So the fact that we measured h, angular momentum, from C, that fact is captured by the fact that we used vector r, right, as the moment arm. It's right there. Right. The fact that it's expressed in B is captured by the equivalent fact that r was expressed in B. So, as an example, you can say that the angular momentum of the aircraft measured from C but expressed in I will be, by definition, well, it needs to be r cross omega dm. But now since it needs to be expressed in I, so the coordinates of each of these vectors would be expressed in I. Right? Just as an example. Okay, so we need to kind of compress all this information into a single expression here for the moment of inertia, right? You know from previous courses that moment of inertia is expressed by the symbol I. Now this moment of inertia is measured from C using R, but expressed in B, so we're going to use the same notation, right? And so here's where we are at. We get that the angular momentum of the aircraft measured from C expressed in B is now equal to the inertia. So that's what we were looking for, right? In the kinetic equations, we need the inertia. We finally pulled it out. Inertia measured from C expressed in B times omega with respect to I. We have been dropping that superscript expressed in B. Just want to point out, as it's done in the notes, this is where it's, sorry, that's a typo, measured, and this is where it's expressed. Okay. And the various elements of the inertia matrix are here, right? So a compact way of writing this matrix is I11, I12, I13, right? And for example, I22 is from over there minus integral x squared plus z squared. I probably should check this sign here. Maybe these negative signs, this extra sign should not be there, but you can go back and check that in the type notes as well, right? So according to what I have here on the board right now, that's I22 integral. Is that now one thing you will notice for this inertia matrix is that it's symmetric, right? Matrix is symmetric because you pick any off-diagonal term, it matches its counterpart on the other side of the diagonal. Right. So look at I21 from here is to 1 is that yx dm integral over b, the body. But I12 is xy dm, which is the same thing. Right. So this inertia matrix is symmetric. It has huge consequences. We'll see that soon further down in this lecture. Okay, so where are we in terms of the overall development of the Eulers equations? Remember, we are trying to write the angular momentum with respect to the origin. Right? We're caught up by the center of mass right now, but we had that HC is equal to mRC cross RC dot plus HO is that, right? Now we found an expression for HC. So we're going to go back here and everything now expressed in B. So we have, based on the developments that we did past few minutes, we extracted the inertia. The angular momentum of the aircraft measured from O, expressed in the frame B frame, is RC expressed in the B frame plus that term expressed in the B frame, but we found a nice expression for it. And of course, this is the inertial derivative, so we can use the transport theorem there as well. Okay. So you can throw that in here. And this is the expression that we have. Okay. Okay, so remember that we're trying to do Eulerian mechanics here, which requires the development of the kinetic equation. So we'll have to differentiate this term, right? Euler's equation was what? H dot is equal to L. So far we are still building H. We're going to differentiate it at some point. But before I go there, I want to take a couple of detours. We're going to talk about two well-known results regarding the inertia matrix. So I want to focus on that a little bit. So, like I said, we're going to take two detours. So the first detour is the following. Okay. Detour number one. Now, this is from the transport theorem, right? So assume that the center of mass as seen by the body frame is not moving. Okay? So its body velocity of the center of mass is 0. We're going to make that assumption. This is not the reality or the general case. This is a special case, an assumption. You just want to consider that scenario. So what happens then is that the inertial derivative of the center of mass as expressed in the body frame is nothing but omega cross r. Right? And let's throw that back up there.
Sorry.
Do you have something to do?
Yeah, should be reserved. Sorry.
12:30 it says.
12:30? Should have been modified to be 12.
Okay. It says 12:30 right now, but that's
Oh,
all
really?
right.
Okay, all
That's
right.
okay.
Well-
Come on in.
All right. My apologies.
Alright, so sorry about that disruption. Just move to a different room. Okay, so we have derived so far this basic equation. Expressed in the B frame is the particle part plus the inertia measured from C expressed in B. Okay. And we are looking at this term right here. So the inertial derivative is the body derivative plus the compensation from the transport theorem. Right. So if you remember, I said before in the previous session that in the previous room that we're going to take two detours, right? Before we take the differentiate this term or the angular momentum term in general to get the Eulers equation, which is h dot is equal to L. So we're going to get there, but we're going to take two detours that will look into the properties of the inertia matrix. So the first detour is that we're going to consider a case where the center of mass as seen by the body frame, as measured by the body frame, is not moving. Right? So what happens then is that the inertial derivative is simply that, and if you want to plug that back up there, over here, then so plug that into, call this equation 2. So use in 2 above, and we get that the angular momentum of the aircraft measured from the origin expressed in the B frame is m or c b cross with now just this part here, omega b cross r c b plus that. And we do the same trick again. This is a vector operation. We're going to transform that into a matrix operation, but before that we're going to flip the order of this cross product, and so that brings out a negative sign, and we have the two skew symmetric matrices associated with the RC vector, RCB vector rather. And now note that this is a common term, right, the omega b. So we can pull that out, and what we get is that the angular momentum measured about O is that which we have now in terms of a matrix of integrals minus this term skew symmetric, skew symmetric. Okay, this is what we have. Great. So, if you stare at this equation a little bit, right, and compare this is equal to that with something else that we found recently, right? Compare that with what we just found, that the angular momentum of the aircraft expressed in the body frame measured at C can be written as that. We just did that, right? So motivated by that knowledge now, we are going to propose that if the angular momentum of the aircraft was now instead measured from O, not C, but expressed in the B frame, can be written, this is a proposal, right, as in similar form, inertia measured from O expressed in B, omega B. And now if we compare that proposal with what we just found, under this assumption, of course, right? Under the assumption that the center of mass as measured by the body frame is static, then we see that the inertia matrix of the aircraft measured from O expressed in B must be nothing but this. And that relationship is a well-known relationship used in a lot of undergraduate textbooks and many graduate textbooks as well, under the name of parallel axis theorem. So it's, you know, it's presented in a different way, but that's what the origin is. And again, something that textbooks miss a lot, there is an assumption behind that relationship, right? Don't just use this relationship as a blanket result that applies to everywhere. It only holds under this assumption. So that is one nice property we see about the inertia matrix, that depending on where it is measured from, if you can find a relationship like that, you know, you can use the parallel axis theorem for two different points like O and C, and relate the inertia matrices that would be computed from those points. So that's detour 1. Great. So the next detour is much more important and relevant to us in our developments here. So we just found ICB, right? This is the inertia matrix of aircraft measured from C and expressed in B, right? And I have stated already multiple times in this very lecture that we are going to be mostly interested in things measured from C, especially as it pertains to properties of the aircraft, right? This is a property of the aircraft, it's inertia of the aircraft, and the most relevant point when it comes to measuring such properties is the center of mass of the aircraft, right? However, there may be a need to express it somewhere else, right? So, if you remember, the inertia matrix was what? That's what the inertia matrix was. Of course, we needed things to be expressed somewhere because the skew symmetric matrix needs components. So that's what we had, right? Now, the question that we're going to ask in this detour is, what if I wanted to use the components of this relative vector R not expressed in the B frame but in the I frame? Suppose that's what we are interested in. So the question is, if I change the reference frame if I go from B to I, then what is the inertia matrix measured from C but expressed in the I frame? Okay. So to get the answer, we're gonna fall back to our old friend, which is rotational coordinate transformations. So here's the basic relationship we have, right? We know that, expressed in the B frame. Now we know that this, the left-hand side, is a vector, right? It's the angular momentum vector. And we know how angular momentum, how vectors transform when you go from one frame to another, so long as the frames are concentric, right? We use the DCM. So now, if we were to express this angular momentum vector measured from C in the I frame, then we would naturally assume that it would be of the form, the inertia matrix measured from C but expressed in I, and the angular momentum vector, the angular rate vector also expressed in I. Right? Now we know how to relate these two entities. Those are just two vectors in two different concentric reference frames. Right? So let's do that. So we have HCI RIB, HCB, but of course this is RBI transpose, because the inverse is transpose for orthogonal matrices. And this we know, right? ICB, we just found this. Okay, so we are getting there. We want HCI to be inertia matrix times omega I. What we have is omega B. So again, we know how to transform vectors. So let's transform the omega vector from I to B, or from B to I. That's easy again. This is omega B, vector transformation. And so we're set, right? Just gonna get this out. This must be at what we were looking for. The inertia matrix measured from C, expressed in I, must be the inertia matrix measured from C, expressed in B, related as RBI, I suppose. So for those of you who are familiar with linear algebra concepts like vector spaces and similarity transformations and so on, this relationship between two matrices expressed in a different coordinate systems is known as similarity transformation. So we look at this in detail in the new math course that has been introduced in the department. We talk about vector transformations, but how do matrices transform from one coordinate frame to another? And we are seeing a glimpse of that when you go from B to I. A matrix that was originally computed in the B frame would transform to the I frame through that so-called similarity transformation. Okay, so what we found is that when you go from one frame to another, when you go from, say, I to B, and we know that the transformation is RBI, then vectors, so vectors transform as follows from I to B. Take any vector V to transform as that. Okay. But matrices that that are computed in these two frames would transform through so-called similarity transformations. So we just got an example for I. So let's do the same. If you start from I and you have to go to B, then that relationship would flip. You'd get RBI, ICI, RBI transpose. This is a vector transformation, and this is the matrix transformation from I to B. Okay. So this may seem like a pointless exercise right now, but it can lead to something extremely substantial and of great consequence to our ultimate objective here, which is to develop the Eulers equations of rotational motion. Right? So again, go back to what we were trying to do here. This is the objective. I would at some point want to differentiate this equation, right? I want to differentiate this equation, right? And then we'll open it up and expand it. So at that point, it will become the role of this detour right now that we're looking at right now will become clear. So the question that we can immediately ask here is that if you look at a generic body frame, right, then you will get a matrix full of terms and it's going to make this a pretty full expression. We can look at what we've just done here and we can ask the following important question. We know now how to transform the inertia matrix from one frame to another through these similarity transformations, right? So the question that we want to ask right now is, does there exist a special body frame, B star, in which the inertia matrix I, so I expressed in the body frame, but still measured from C, right? Our reference point is fixed at C, but now it's expressed in this special body frame. So does there exist this special body frame B star in which the inertia matrix is diagonal? So we can kill all these off-diagonal terms and make it nice and clean, look something like this, such that the inertia matrix measured from C expressed in B star would have this nice clean form. And as you can imagine, it would make our life much easier when we go and differentiate that basic equation. Right? Okay, so how would you go about solving this problem? This is kind of an inverse problem, right? We are looking for a reference frame in which the matrix would have a nice desirable structure. So here's what we're going to do. What we can do is, we can start from an arbitrary body frame. And then we're going to try and find a transformation that leads us from this arbitrary body frame to that special body frame, right? So in aircraft, your standard body frame is the x-axis through the nose, y-axis through the right wing, and z-axis down, right? So you can start with that basic body frame, and once you have that starting point, compute the inertia matrix in that frame. So that's 1 and 2, compute, so call this B, compute the inertia matrix from point C expressed in B, right? And now step 3 is determine the transformation, the rotation matrix from B to B star, such that IC B star is diagonal. That seems pretty reasonable. Find some starting point, some convenient body frame, compute the inertia matrix there, and then find the path to that special body frame. Okay? So, now we need to find this matrix, right? So we need to assume a structure for it. So that's not too hard. We can let this DCM have 3 columns. It does have 3 columns, call them C1, C2, C3. And we know the relationship between these 2 matrices, right? It's the similarity transformation. So we have IC B we know that. Now, we have found this, right? That was step 2. We know what this should look like. It needs to be diagonal. And we have proposed a structure for the other term in there, right? So let's all throw that, before I throw everything in there, I'm gonna pull this over on this side, right? And so that can be done by simply multiplying both sides by that term, because this transposes the inverse of that. These will neutralize, and so this was a right. So this was a post multiplication. So I just post multiply by RBB star, and this goes away, and we are left with ICB. Now I'm going to throw in the structure C1, C2, C3 is equal to C1, C2, C3, and I know the structure of this. The desired structure is diagonal. Just a 0. Get that. So this is a matrix multiplied by another matrix. We can get 3 columns here that we can compare, right? So I can, or when you do the multiplication, the first column of the multiplied matrix is, C1, and then ICB C2, and ICB C3 is equal to, carry out this multiplication here, I1 C1 to C2, and I3 C3. Right? And so the columns should match on both ends, and so here's what we get. We're trying to solve for C1, C2, and C3. So we get that comparing the columns. Well, let's just look at one equation. The same equation should hold for 2 and 3 as well. Right? So this is a known matrix. We just found it starting from some convenient body frame. This is an unknown column vector. This is an unknown scalar, right? It's part of the diagonal inertia matrix, and it's that same column vector. So for any of you who have done even a little bit of eigenvalue problems, you see that this is nothing but the eigenvalue problem for this known matrix. Which is known, right? And so the final step of this procedure to find that magic body frame in which the inertia matrix is diagonal is to simply solve the eigenvalue problem for the inertia matrix you just found, right? That will give you both the eigenvalues, which are these scalars, and the eigenvectors, which are these columns, right? You can normalize those eigenvectors to be unit vectors. That's not hard to do, and you can then construct RBB star as C1, C2, C3, as these are the 3 eigenvectors of So you get giving I C B star as R B B star transpose I C B equal to, you don't even have to do this because once you solve the eigenvalue problem, you know that this inertia matrix is going to be diagonal and the diagonal entries are going to be the eigenvalues, right? So of course, for some of you who do have some experience with eigenvalue problems, you might be wondering whether you can actually solve this problem or not, right? You know that eigenvalue problems, eigenvalues can always be found because they are just the solution of the characteristic equation, right? And the characteristic equation is nothing but a root solving problem. So solving the characteristic equation becomes a root solving problem. So you can always find those numbers. But the question is, how do you know that these columns are going to be orthogonal to each other? That we need that to construct this matrix, because this is supposed to be a DCM, and DCM has special properties, right? It is an orthogonal matrix. So how do you know that when you solve the eigenvalue problem, the eigenvectors you get, when you line them up as columns of a matrix, you will get an orthogonal matrix? So this is where the fact that the inertia matrix is symmetric plays in, okay? So if you go and look at the theory of the eigenvalue problem, you'll see that if your matrix is symmetric, then you are guaranteed to get orthogonal eigenvectors, and they will all be, so well, they're orthogonal, so they're linearly independent, right? So when you line them up like that, you get an orthogonal matrix. Okay, so symmetry of ICB, it's a valid inertia matrix, it's going to be symmetric no matter what body frame it's measured in from. Guarantees existence of R BB star, and therefore essentially it guarantees the existence of this special body frame in which the inertia matrix is diagonal, right? So given any structure, you're guaranteed to find this special body frame known as the principal body axis, in which the inertia matrix of that object is diagonal. Okay, this is a very important result. So this is a guaranteed true or false question in the exam, that for any arbitrary object, right? So we can assume it's rigid. Assuming the object is rigid, it is guaranteed that in some special body frame, the inertia matrix will be diagonal. And the answer is true because you can start with an arbitrary body frame, find the inertia matrix, and then solve its eigenvalue problem to get that special reference frame. Okay. Great. Okay, so we have found this principal body frame. So, well, this is a great result, but what happens is that the frame that we talked about initially, right, the body frame that is used for aircraft through the nose, right wing and down, that body frame unfortunately is not the principal body frame. So you would expect that to find the principal body frame, well, the principal body frame would require the object to be perfectly symmetric about it, right? So if you have an aircraft like that, right, about these axes that you defined, the object would need to be symmetric for the off-diagonal terms of the inertia matrix to be zero, right? So if you have a cigar-shaped object, right? So consider only the fuselage and assume it's cigar-shaped, right? Then this is an axis of symmetry. This is an axis of symmetry, and so is that. Okay. So if you have axes of symmetry of the object, if the mass is evenly distributed, that's the other thing, then those off-diagonal terms will be zero. But for aircraft, the aircraft is close to symmetric but not purely symmetric. So when you see the inertia matrix about the commonly used body frame, right? Through the nose, right down. That inertia matrix won't be diagonal. It's going to be close to diagonal. Law of diagonal terms will be close to 0 or orders of magnitude less than the diagonal terms, but they will be not diagonal. Okay, so we do not go into the principal body frame, even though it does exist, because of other issues. But you should know that it exists and it's there if you wanted to use it. Okay. So we are now set. This is the end of the detour. We're going to go back, revisit our angular momentum equation, and then we are going to differentiate it. Right? So our angular momentum equation was, so if you remember, there was one in the O measured with respect to O, and so it was that, plus for rigid objects. Now I'm going to make a big important note here. From this point on, we will only measure angular momentum from C. And so this part. It's good to know that the angular momentum of the aircraft measured from O, expressed in B, that's not so important, but measured from O is related to the angular momentum measured from C through this relationship, right? We have to add in this particle angular momentum of the center of mass. But from this point on, we are going to only be concerned with that, okay? So our object of interest is the angular momentum of the aircraft measured from C, expressed in B, right? And we just found this to be equal to and I'm going to state that this B frame may not be the principal axis frame, at least for the first part of the development here, right? We can make some assumptions later that, oh, it's close to diagonal and so on, but let's just assume it's not, the inertia matrix is not diagonal in this B frame. Okay. Great. Now, we are going to differentiate this equation, right? The good thing is that the reference point is the center of mass, and if you go back to the very beginning of the lecture, we said that for the reference point located at center of mass, the rate of change of angular momentum, inertial rate of change, is equal to only the moments measured from that point. There is no compensation term needed. And of course I need to express this in B as well, consistent. This is Eulers equation that we are trying to expand now. For, remember, so in this picture right here, right? P equal to C. Great. So plug in this over there to the left hand side, right? This is the inertial derivative. So the inertial derivative of that is equal to the inertial derivative of what we just found right here. And we don't like that because this is measured in the body frame, right? It's well, it's expressed in the body frame and it's measured with something on the body. That's the center of mass. That's this matrix, right? So you can transform this to derivatives in the body frame using the transport theorem. And then compensate for it. Okay. So this is, there are two terms here. This is easy. This is just a cross product. You know what to do here, right? It's a cross product. We can write this in skew symmetric form. So I'm going to call this T1, this whole guy here, plus this term, omega B, skew symmetric matrix associated with that, and IB C omega B. Okay. Now T1. So apply the chain rule, you get IC body derivative plus ICB. Now here's the important thing here. This matrix contains terms that have been expressed in the body frame, right? So it has, so for example, ICB, the term 1 comma 1. This is integral xy dn. Remember, xy was what? The coordinates of the arc vector. Right? So if I take the derivative of this term while sitting in the body frame, right? This vector is not changing. So its body components will not change as seen from the body frame, right? So this derivative measured in the body of the inertia matrix is going to be 0 for rigid objects. This is the body rate, right? I'm not saying the inertial rate of this term will be 0. We are saying that the body rate will be 0, right? Because the object is rigid, x should not be changing. For an elemental mass, as measured from the body frame over time, it should not be changing. It will change when you go from one element to another, and that's fine, right? But each element should be relative to the other element, should be at the same location at all times. So its time rate, as seen by the body frame, should be 0, right? So that's something great that happens, right? You get this big simplification, and so T1 is simply inertia times omega dot. Right. So put that back in here. Right. Therefore, the inertial derivative of angular momentum is ICB omega dot plus what we got here, omega cross omega. Great. And we know that this is equal to so that's it. This is our kinetic equation for rotational motion. It says that the rate of change of angular momentum, the inertial rate of change of the angular momentum, equals the torque or the external moment, right? And on the kinematic side, we have inertia, rate of change of angular velocity, so this is angular acceleration, and then this compensation term that came about because of the transport theorem. So we can expand this now, right? These are matrices. These are a bunch of matrix multiplications. So we can expand this, and this is where you appreciate that when you try and expand this into the individual component equations, it would be much easier if things would be much easier if this I matrix was diagonal, right? So we're going to make that assumption for the purpose of doing the expansion in the classroom setting, because You can have a full matrix here, and you can keep writing term after term, and this matrix multiplication just fills up space and time, right? So for the purposes of illustration, we're going to assume that. So assume now that this B frame is the principal body axis, such that the inertia matrix is diagonal. That's not really true for aircraft, but I mean, it's not such a big deal because you're going to implement this on a computer anyway, and you can ask the computer to do that multiplication for you, right? You don't have to see what those equations look like, and they are there in the notes as well, the type notes. But for right here, we're going to do this multiplication assuming a diagonal matrix. So this term is I1, I2, I3, and in the notes that you have with you, I have used omega 1, 2, 3, but you know, it's P, Q, R as well, it's the same thing. Right? So this is P dot, Q dot, R dot. And then this is your skew symmetric matrix, so minus R, Q, R, 0, minus P, minus Q, P, 0, and then I1, and then that finally is equal to, let's call this L1, L2, L3. The three moments, sorry, this is expressed in the B frame. So those are the components of the B frame, right? And so you can carry out this multiplication and get the three equations out of there. As you can see, things are easy now because this is a diagonal matrix, so there are a lot of zeros in the multiplication. So when you do that, here's what we get. So open this up, and we get I1 P dot is equal to L1 plus I2 Q dot these are the three Eulers equation of rotational motion for rigid objects in the principal body frame. It's much more complicated. There'll be a bunch of different terms involving the cross terms, the cross products of inertia. It's much more complicated in a non-principal frame. In fact, this is good because it's decoupled, right? I get P dot is equal to something that does not involve Q dot or R dot, right? So you can divide by the inertia terms and separate out P dot is equal to something, Q dot is that, and R dot is that, and then get all the equations. So that's the kinetics, right? Remember that we have already derived the kinematic equation, right? So this is the kinetic, combine it with kinematics. Remember, omega dot was equal to that B matrix times theta, and the theta is nothing but three Euler angles, derivatives, right? So, and that was in the B frame. So this would be, I'm sorry, this is not omega dot, it's omega, it's equal to that. So when you invert this equation, you get psi dot theta dot v dot is equal to B inverse times PQR, where PQR have been obtained by integrating those equations. Right? So you have to solve this simultaneously, of course. So here's the kinetic equation of rotational motion, and here's the kinematic equation of rotational motion. And once you get psi theta phi, you can get the rotational position, if you remember, which is nothing but RBI matrix at all times. This was elemental 1, 2, 3. Right, and you're done. These are the accelerations. When you integrate them, you get velocities, PQR. These are the positions. When you integrate these right here, using the velocities that you just found, you get the positions. Throw them into the RBI matrix, which is the real position, attitude. There's your attitude. Okay. So to end this lecture, I just want to do a grand summary of all the equations of motion, okay, that we have and that you will need to write a code for to integrate and get your 6 degree of freedom simulator for aircraft motion. So here's a grand summary. This is the last page of the written notes. Complete dynamics of an aircraft, rigid. Okay. There are 6 degrees of freedom. 3 in translation, and 3 in rotation. Okay. Here's the picture, and of course there's a body frame that is attached to the aircraft, right? It is located at O, but it's attached to the aircraft in the sense it's constrained to move, turn with it. So the rate of the body frame with respect to the inertial frame is omega. Great. So translational motion. Position is RC, because translation is translation of the center of mass. Okay. And you can express it in the B frame if you like. This is RC expressed in B. Velocity. Now we are only interested right now in the inertial velocity. It's the velocity of the center of mass. Okay. And so this can be written as, using the transport theorem, and of course the acceleration. Inertial acceleration is the inertial derivative of the inertial velocity. Expressing this in the B frame to be consistent. Okay, and we did this, right? If you remember, this will be ACB. Oh, sorry. Plus Coriolis acceleration plus the transport acceleration final term, which involves the angular rate, angular velocity derivative of the angular acceleration. Okay. And then finally, the kinetic equation comes from Newtonian mechanics. Is that force equals mass times. So I'll express this in the B frame. Acceleration. This is which is that. Okay. So this is kinematics. This is kinetic equation. Each of these vectors have three components, and therefore those are the 3 degrees of freedom of translational motion. Okay. So that's the 3 degrees of freedom associated with translation. I'm going to get this out now and finish with rotation. I'm going to do the same thing. Rotation. Position. This is RBI, right? It's the attitude.